Hey everyone, what we're looking at here is Chapter 9, Rotational Motion. So everything we've done in the past has been in 1 or 2 or 3 dimensions. So we've gone in the X, Y, or Z plane, but now we're going to take everything we've talked about and spin everything we've ever done. So if you look here, most things in life don't just go in straight lines. Most things do travel in circles, so they have this rotational aspect that we have to focus on. And the first thing we want to focus on is the difference between rotating and revolving. So I'll show you 2 clips here. Tell me which one is rotating and which one is revolving. And if you look at those 2 clips, the difference is where you put the axis. When the kids were rotating around that shovel in the yard, that axis was out away from them. But whenever the wheel was revolving, the axis was right in the middle. So where you put the axis is really just the difference between rotation and revolution. You can still have things measured in rotations per minute or revolutions per minute or per second, but we have to define where this axis is, and the axis can be arbitrary for any problem you want. You pick where the axis point is. And when we define rotation, we have to define things like frequencies or time periods, and we've talked about these a little bit in the past with going through circles. Time period being the time for one cycle to occur, how long it takes you to go around the circle once, while frequency is just how often that cycle occurs, how many cycles per second. The units for time period are just any unit of time: seconds, minutes, hours, days, years. While frequencies, we often do cycles per second, so things, anything per second, or you might see it written as a hertz. Frequencies are measured in hertz. Hz is your abbreviation for it, and it just tells you how often something's occurring. The Earth does rotate. The Earth does rotate on its axis, and we do pivot on almost one star. You can see right there in the center, and that is Polaris, our pole star. So every day the Earth does rotate on its axis, but the Earth is also revolving. It revolves around the sun. So not only is it doing a rotation every day, it's also doing a revolution every year. And even our star is doing a revolution around the center of our galaxy. So depending on how far back we pull ourselves, we can give ourselves different points of axis to define our rotation. And with the rotational kinematics, like we saw in class today, the distance around the curved path is called the arc length. And arc length, they give it a variable s. When you are rotating, you sweep out angles of theta as you start to travel that arc length. So as you start to go around the circle, not only are you walking a distance around the edge of the circle, but you're also sweeping out an angle theta. And that theta we're going to call our angular displacement. And what we saw in the lab today, the ratio of arc length over radius is what our angular displacement is measured in, or our theta. And if you look, arc length will be measured in meters or inches or miles, and our radius would be measured in inches or meters or miles. So when you divide 2 distances over each other, you get no unit. However, angles need to be measured in something, so instead of measuring them with no unit, we give them the unit of radian. And we've got 2 directions we talked about in class: the clockwise direction and the counterclockwise direction, all based off your right hand rule. So with the right hand, you want to see how your thumb is pointing, curl your fingers in the direction of the rotation, and if that thumb is pointing out towards you, that is a counterclockwise rotation or positive. And if your thumb points inwards towards the page or the board, then we have a clockwise rotation. And with that angular motion, we talked about the angular displacement being measured in radians or degrees, revolutions, rotations, whatever unit you'd want there. But whenever you do this, we want to make sure that our final angular displacement gets into radians. So knowing that 2 pi radians will get you around an entire circle, 1 full radian is not just 1 full spin. It's about 57 degrees of your circle compared to the full circle being 360. Angular velocity is defined as our angular displacement over time. And angular acceleration is defined as our angular velocity changing with time. So we have new variables for those as well. We have omega being our angular velocity equation, and we have alpha being our angular acceleration equation. So just like we had in the past, we had displacement over time being our normal straight line velocity. Now we have omega being our rotational or our angular velocity, because people are now going to change a displacement of our theta as time goes on. And units for that would be the radian per second. So how many radians have we traveled every single second? If we see ourselves changing our omega with time, or changing our angular velocity with time, that means we've gone through an angular acceleration. And instead of using A, we now use alpha for our angular acceleration. So that means that our radians per second are changing every second. Or we can write this as radians per second squared. And since alpha is the derivative of angular velocity with time, what you could just do is the second derivative of theta versus time to give you alpha as well. So this same rules apply for angular displacement as applied to regular linear displacement. And since we know that these equations all follow the same rules we did before, when things are accelerating in our rotational units, that means we can just transform all of our kinematics equations into angular kinematics equations. The first one is omega f equals omega o plus alpha t. That's the same as vf equals vo plus at, like we did before. We can have our change in displacement, our change in theta, be omega t plus 1/2 alpha t squared. And we can go one step further and say that our final omega squared equals our initial omega squared plus 2 alpha times theta. So all three of our kinematics equations are back in play. They work the same as they did before, but this time you're going to be talking about something spinning in a circle. And how many spins does it make would be the displacement the object travels. How fast that object is spinning would be the omega. And how quickly that velocity is changing would be our alpha. And with each rotational concept, each piece of something rotating in a circle will travel the same omega. It'll travel the same theta over the same amount of time, which means that all objects rotating will have the same rotational speed, which is something they like to trip you up on. However, different points on the circle will have different linear motions based on how far they are from the center point. So a linear velocity would be how fast does an object want to leave tangent to the circle. We said that objects don't like rotating and don't like staying in circular motion. They want to leave in straight line motion. So let's transform our rotating velocity into a linear velocity. So in that good old-fashioned linear velocity is our displacement over time. And since our displacement around the circle, if we were running around a circle, would be the arc length that we're traveling, what we know is that arc length is r d theta over time. The radius of the circle never changes, but what does change as our arc length changes is our theta. And if you look at d theta over time there is something we know. It is omega. So if I want to find the linear tangential straight line velocity of an object, it's really just radius multiplied by omega. And we know that the units for velocity are meters per second. That means that r multiplied by omega must give us meters per second. Well, radius is simple. That's got to be in meters. And omega is in radians per second. The nice thing about radians is radians are really just a placeholder for your units. If a real unit comes along, it can trump and replace the radian unit to give you your new units. So a meter times a radian just really gives you meters per second. The radian is your rotational speed. Also, as we go around a circle, we know that we can linearly accelerate. If something starts to rotate faster, not only will that rotational speed increase, but the linear speed will increase. And if the linear speed increases with time, that means that something has been linearly accelerated, has tangentially accelerated. So let's look at the definition of acceleration versus time. So since straight line tangential acceleration is dv over dt, we know that straight line velocity now is r omega. And from before, if omega is changing with time, we know that we are accelerating, angularly accelerating, which means that straight line acceleration can just be found by r alpha. And with r and alpha there, we can do the same thing with our units. We know that radius is meters, alpha is radians per second squared. The meter will replace the radian, and you'll be left with meters per second squared. So a straight line tangential acceleration can just be found by r alpha, as seen here. So it's a meter times a rad per second squared. Also, one other thing they might ask you is when you're going in a circle, not only could you linearly accelerate, but you always centripetally accelerate, which means how quickly your direction changes. So we can translate centripetal acceleration, take our rotating equations, and get a centripetal equation. So centripetal acceleration we know is v squared over r, and in this case, v is now r omega, and we're going to divide that by radius. So when we do this, you'll get r squared omega squared on top, which will leave you r omega squared. And if you check the units on that for centripetal acceleration, omega is meters or radians per second, but now you're squaring that, so radian squared per second squared, and the meter still replaces the radian squared. So you will still get, for centripetal acceleration, meters per second squared. So everything we've done before in our linear accelerating units, we can now translate into our rotational units by using the rotational kinematics, or if they want you to find the straight line acceleration velocity or centripetal acceleration, we now have a way to relate the straight line motion with our rotating motion.